Hello everyone, my name is Dhruv Mulay and I am a research assistant with Robing Dong's group at the University of Victoria. And today I'd like to give a talk on why deep cavities in gas and dust, simulations versus observations. So let's just launch into a bit of an introduction. So there's been a lot of recent work on high resolution imaging of disks in gas, tracers like 12 or 13 CO, and dust, millimeter continuum and scattered light with instruments like SPHERE and ALMA. Now this has allowed us to probe various features, substructures, and protoplanetary disks with increasing degrees of accuracy, such as planet-driven spiral arms and Rossby wave instability vortices, to name a few. Now one particular area of interest for these high-resolution studies is transition disk cavities in gas and dust. Now that's something that's particularly interesting for me, so in this talk I'll base it on two papers. One was some work that we did last year on how planets carve different sized cavities in gas and dust in these transition disks. It was inspired by PDS-70, which before the discovery by Sebastian Haffert et al. In 2019 was thought to have only a single planet. So that was the motivation for that work. And we've tied that theoretical work to some more recent observational work on substructures in protoplanetary disks led by Nienke van der Marel. So let's talk about it. What is a transition disk? So it's essentially any disk where the innermost, hottest part of the disk has been removed. So this was inferred in the past through studies of SEDs, where there was a dip in the SED where the hot inner region of the disk would have been represented. However, more recently, we've been able to perform high-resolution imaging, and we're able to see these inner disks more clearly. There have been various interpretations proposed for why these inner disks are cleared. One is that grains grow and coagulate, and therefore the surface area that they radiate off of is smaller, so they become effectively less luminous, so they're not clearly seen. Another idea is photoevaporation, that a lot of this material is simply just ablated away by ultraviolet. But one idea that's gained increasing prominence in recent years, in addition to these others, is that these cavities may have been carved by disk-planet interaction. So that's something that motivated our work on PDS-70, which we'll launch into. So PDS-70 was studied by Miriam Kepler et al. In 2018. It's among the first systems where there's a transition disk hosting a planet. So PDS-70b, the planet in the system, is located at 22 AU. It's a super Jupiter, and it sits in a gas cavity that's around 33 AU wide, as well as a dust cavity that's something like 65 AU wide. So let's see how PDS-70b, according to prevailing theories, may have carved this gap. So if you look at gap opening theory, it's something that's gone back decades. And what they do is they decompose the planetary potential into various Fourier modes. And these Fourier modes actually are resonant with different locations in the disk, known as Lindblad resonances. So when a planet has these Fourier modes exciting, like being forced into a gaseous disk, what you get are sound waves. And these sound waves, after a few cycles, they'll deposit their angular momentum in a particular location. For material on the outside of the planet's semi-major axis, you get a positive impulse, so that material flies further outward. Whereas material on the inside of the planet's semi-major axis, you get material falling further inward because it received a negative impulse. So what implications does this have for observations? So these gaps tend to have pressure maxima at their outside, located around 50 to 100% of the planet's semi-major axis away from the semi-major axis. So at these pressure maxima, dust-gas drag means that dust is going to collect there. So in continuum, you'd see a bright dust ring at that location. Whereas the gas gap is considerably narrower, maybe only about 25% of the planet's semi-major axis. So that's something that would be visible in a tracer like 12 or 13 CO. How would this apply to PDS-70? the planet at 22 AU, we'd get a gas cavity at something like 28 AU and a dust cavity at something like 44 AU. However, clearly this is not something that we observe. In actuality, what we find is a gas cavity at 33 AU, but the dust cavity a staggering 65 AU radius from the star. This is twice as wide as it should be, and there's no explanation just within the ordinary gap opening theory with a fixed planet. But what if the planet were actually eccentric? That's the hypothesis we sought to investigate with our study. So we simulated the disk using the Penguin hydrodynamics codes GPU accelerated, written by Jeffrey Fung, my advisor for this work. The fiducial simulation that we ran, we started with a 10 Earth mass core, which could accrete material from the disk and could also evolve in semi-major axis and eccentricity. In other words, migrate. We ran this for about 5 megayears, which is something like the lifetime of a protoplanetary-disk. We tested over 100 different alternative models, and none ended up really resembling a transition cavity. For the planets, we tested fixed versus moving, migrating planets. Turns out we needed moving planets in order to create the wide gap. We tested accreting versus non-accreting planets. We needed accreting planets in order for the gap to be sufficiently deep. Likewise, we tested cold disks, which were just heated by stellar radiation, as well as hot disks, in which we had additional heating sources representing some source of active heating. Turns out the cold disk better resembles a lot of these transition cavities. Viscosity, at least PDS-70 in particular, doesn't have huge asymmetries, so we wanted to choose a viscosity that would parameterize processes that would damp these asymmetries somewhat. So we chose an alpha of 10 to the minus 3 as opposed to something smaller. How did the planet evolve in our simulations? So for about 3 megayears, the planet grew accreted material from a super Earth core into a super Jupiter giant. But then when the mass ratio reached something like 3 times 10 to the minus 3, or 2.5 Jupiter masses given the mass of the star PDS-70, some higher order eccentric Lindblad resonances actually pumped up the eccentricity of the disk and planet. And as you can see in the lower right panel, that eccentricity for the planet at least grew as an instability. And this enabled the planet to accrete and clear a wide swath of the disk. And this is a result that holds across a wide range of surface density, except what happens when you have a higher surface density is you reach that critical cutoff mass of eccentricity sooner, so the whole evolution happens a lot faster. So that's the main difference between these 3 white, orange, and red runs here. So let's just take a look at our fiducial run and see how it evolves. As you can see, the planet starts out just carving a normal, narrow gap, but it's accreting material from the disk, so you can see the gap slowly becomes wider. And once you reach around 3 megayears, you can start to see some eccentricity in the disk start to grow. Now this eccentricity starts getting exchanged with the planet. Now the planet can eat a much wider swath of the disk, can clear out a much wider range, giving rise to a transition disk similar to those observed. A planet pretty close in, a pretty wide gap in gas, a pressure maximum, which would create a dust ring around 63 AU. So how does this stack up compared to a fixed planet run, for instance? So that planet that I just showed in the fiducial run capped out around 4 Jupiter masses for reference. But if you test a fixed planet with, say, 2 Jupiter masses, 4 Jupiter masses, or 8 Jupiter masses, you find not only a much narrower transition cavity, but you also find that the separation between the optically thin gas cavity, where the density of gas, surface density, goes below 10 to the minus 2 grams per centimeter squared, the optically thin gas cavity is actually very close to that outer pressure ring. But in many of these transition cavities, as we'll see in a little bit, observationally there's a wide separation between these. And if you want to actually produce that wide separation with a circular planet, you'd need very, very large planets in the brown-dwarf regime. So in essence, what we've found is that eccentricity creates a wide separation between your optically thin gas cavity and the dust trapping pressure maximum at the outside. So again, how does this stack up with observations? So turns out Facchini et al. In 2017 studied the relationship between planet mass and gap width and the separation between your outer dust ring and your gas gap width. And it turns out to produce a wide separation between gas and dust gaps, you need, for a circular fixed planet, you need very, very high planet mass. So, in fact, the companion mass may even be in the brown dwarf regime, as you can see. Now, Nienke van der Marel et al., the second paper that we're talking about, they studied a lot of different transition disks, observed them, and found that the separation between gas and dust cavities were indeed commensurate with brown dwarf sized companions. Unless we assume that eccentric super Jupiter planets could actually carve these companions. That's the alternative. And it's an alternative that's favored because the occurrence rates of brown dwarfs simply aren't favorable enough to create all these transition disks that we observe. So some conclusions. So if you have companions of around 3 Jupiter mass or higher, they reliably become eccentric. Using accretion, they can carve wide transition cavities similar to those observed. This creates wide separation between gas and dust cavities, which is similar to that actually created by circularly orbiting brown dwarf companions. However, the occurrence rates of these brown dwarfs are actually pretty low compared to super Jupiters, whereas transition disks are actually quite common. So eccentric giant planets indeed may be responsible for a good fraction of these observed transition cavities. Thanks for listening to my talk, and I'd appreciate if you could send me any questions or comments that you may have on these works.